Hey guys, Mr. Riz here to help you out on the first part of the 3.4 notes. So what we're going to be looking at 3.4 is concavity of graphs, and we're going to look at specifically the second derivative. So our objectives here are to determine the intervals in which the function is either concave up or concave down. We're going to find any points of inflections next time, and then we're going to apply the second derivative test to help us find relative extremas on a function. So let's talk about concavity here. A lot of times we can just describe this by looking at the picture, but there is a technical definition. It says let f be differentiable on an open interval of I, so it can be taken the derivative of the whole way through. The graph of f is concave upward on I when f prime is increasing on the interval. So if we look here, this is concave upward because the derivative here is increasing. So you can see it's like starts negative, it gets positive, and then even more positive. So as you move along, the graph, the derivative becomes more positive, positive, positive. It gets higher, higher, higher. The slope does. All right, it's concave down on I when f prime is decreasing on that interval. So if the derivative gets lower, lower, the slope gets lower, lower, and lower as we move along, it's concave down. Now the easiest way is called concavity. If you look, does the graph curve up? That's concave up. Does the graph curve down? That's concave down. If the graph is flat, that is no concavity, or it's just a horizontal line. So how do we determine those? And if we kind of take a look at the graph here, this might be a clue of what we're going to do. So if we're looking at this original graph here, if we want to determine the intervals where it is concave up or concave down, you can look here to see that it does kind of switch. Like right here, it's curved down, and then over on this side, it's curved up. Now, what we could do is look at the derivative graph here, and to see when the derivative stops going down and switches to going up is going to be the point where we switch our concavity. So you can see right here at 0 is on the original graph where it would switch its concavity. Now the key point, if we think about, okay, how do we find this low point on the derivative? Well, we could take the derivative of the derivative, the second derivative, and figure out where this derivative equals 0, or where does the derivative's derivative equals 0. That's actually correct. So what we're going to do here is the second derivative test. So if you think about it, the first derivative test tells us where our graph is going up and where it's going down. So you can see the first derivative, the graph is above, so it's going up, and then it's all below here, it's going down, and then afterwards it's going up. That's the first derivative test. If we were to take the derivative of the derivative, that would tell us the concavity. And so let's do that here. We have the equation here. Now, this equation can be written a couple different ways. You can see over here in the graph, it is 1/3 x cubed. That's probably easier to take the derivative of minus x, but it's the same thing here. So we do have to take the first derivative in order to get the second derivative. All right, so if we take the 3 times it by the 1/3, we get an x squared minus 1. That's this first derivative here. And then if we take the derivative of that, the second derivative, which would be, okay, x squared becomes 2x, and then minus 1 goes away. So the second derivative, maybe I can graph that over here, would just be like so. There is the second derivative. Okay, so first derivative test, we found those critical points by taking the first derivative and figuring out where it crosses the x-axis. The same thing here. If we want to find the critical numbers of the second derivative, we need to set that equal to 0. So let's take the second derivative, set it equal to 0, and that's when x equals 0, which we kind of have already noted there. All right, so we're going to make a second derivative test like we did with the first derivative. So we're going to make our number line here, and we're going to put our critical points on that number line. And our critical point here is just x equals 0. All right, now to determine the concavity, we're going to pick points in the intervals of less than 0 and greater than 0 to determine whether the second derivative is positive or negative. So if I take a number that's less than 0, like -1, and I plug that into the second derivative, so what's 2 times -1? That is -2. That is a negative interval, or that's a negative answer. So that means all of our graphs are going to be concave down. They're negative. It makes a sad face. All right. Next, let's pick a number bigger than 0, like f double prime of, maybe 3. What's 2 times 3? That is 6. 6 is a positive number, so everything after 0 will be positive, concave up. So this is going to be how we answer these problems here for this class here. This is how I think it's easy. We can visually see that on the second derivative, the graph before 0 switches from concave down, and after 0 switches to concave up. And if we look at our graph here, everything before 0 is concave down, everything afterwards is concave up. Okay, so let's do another one for practice, and then we'll look at the homework problems. Okay, so let's try to do this without looking at Desmos, and then we'll go back and look at a graphing calculator to help us out. Okay, so let's see, 6 over x. Okay, so that means we got to take the first derivative, and we got to do the quotient rule for this one. So we got low, x squared plus 3, d high, okay, that's 0, that's kind of nice, minus high, okay, 6, and then d low, the derivative of the bottom is 2x. And then all over low is x squared plus 3. So that means the first derivative is, simplifying, that goes away because it's times 0. We get a negative 12x over, forgot the low, over x squared plus 3 squared. Okay, not too bad. Okay, now what we need to do is to take the second derivative. So we need to get the derivative of the derivative. Now this is why, and this is when we did the whole practice, because of this problem, we do have to do the quotient rule again, but we're going to have to do the chain rule here. This is why we practice using those. This is pretty much like the toughest math I think you guys should be able to do here. All right, so let's do low, which is x squared plus 3 squared, d high, which would be negative 12. And then minus high is negative 12x, and then d low, we got to do the chain rule of. So something squared becomes 2 of that something to the first power, and then we times by the derivative of the inside. The derivative of x squared plus 3 is 2x. Whew, hot dog. All over a x squared plus 3 to the 4th power. Okay, what I like to do next is I like to factor out, because if we look on the top here, we would have, we got an x squared plus 3, we got it squared, we got an x squared plus 3 from this term here, because you think about, we got kind of 2 separate terms. Let's factor that out and cancel one of them from the bottom. So this bottom here, if I take this from 1 away from here, this goes away. If I take 1 away from here, this goes down to 1. And if I take away from the bottom, that goes down to 3. So we got an x squared plus 3 cubed. All right, what does this come up here on the top? We distribute the negative 12. We get negative 12x squared minus 36. And then over here, let's see, the negative times the negative 12 becomes a plus 12. So we really just need to do 12x times 2 times 2x. So let's see, 12 times 2 is 24, times 2x is a positive 48x squared. Okay, so the second derivative here took us a minute to figure it out, but it is, let's see, we add those together, we get a 36x squared minus 36 over our x squared plus 3 cubed. Okay. Let's talk about our second derivative test here. To find the critical numbers of the second derivative, we need to set it equal to 0. Now, since this is a fraction, we set the top equal to 0. And we should also figure out when the bottom cannot equal 0. All right, so if we were going to figure out this top part, we'd add 36 over, divide by 36, and then take the square root, we get plus or minus 1. So we got 2 numbers there, positive and negative 1. Let's figure out what this number could be. Okay, I would cube root 0, it's still 0. Add minus 3 over, it's negative 3. If we take the square root of negative 3, it doesn't work out. So we just have 2 critical numbers. One's at negative 1 and one's at positive 1. Okay, next what we need to do here is to figure out the concavity. So we're going to take different numbers, different intervals, and plug them in. So let's pick a number less than negative 1. Negative 2 sounds like the easiest to me. We're going to plug it back into the second derivative here. So what's 36 times negative 2 squared minus 36 over negative 2 squared plus 3 cubed. Okay, so let's see. The bottom is, we don't really care especially like exactly what the value is, just like, is the top positive and is the bottom positive? That's positive divided by a positive is a positive. Let's just kind of figure out what's going on here. So -2 squared is a positive 4, plus 3 is 7, 7 cubed is some positive number. And on the top here, -2 squared is a positive 4, 4 times 36, and then minus 36 is still positive. Positive divided by a positive is positive. So everything less than -1 would be positive, meaning our graph should be curved up. All right, now we'll pick a number in between -1 and 1. How about 0 and see what that looks like? What's 36 times 0 squared minus 36 over this 0 squared plus 3 cubed? All right, so the bottom here, if we add 3 to 0 and cube it, it's still positive. But on the top here, 0 times 36, that's 0 minus 36, that's a negative number. Negative divided by positive is a negative, so that's going to be concave down. And then, I'm kind of running out of room, so I'll write it here. Pick a number bigger than 1. How about 2? That pretty much just changes a little bit of our graph here, which might not change much since things are getting squared. Bottom's still going to be positive. Now the top here, 36 times 2, okay, 4 times minus 36, that's still positive. Positive divided by a positive is a positive. There we go. So our graph should be concave up, concave down, concave up, and it should switch at -1 to 1. Okay, so let's see if we can kind of verify this. I'm going to go see if I can kind of get a little fancy here. Let's get rid of everything but our answer here. Can I delete? Ooh, that's nice. Maybe I'll try to kind of move this over here. There we go. Okay, so that's our answer. Let's verify this on the Desmos. Get the 9 club here. Let's go through, clear all this old graph stuff out. We got 6 divided by x squared plus 3. Okay, so you know what I'm even going to do on here to plot the points of 1 and 2. Let's look at this one here. So, I don't care. Can I just delete that? I don't think, undo. All right, so here's 1, here's -1, and we can see everything before -1 is it's curving up. In between 1 and 1, it does curve down, and then after 1, it curves up again. So it's all curved up. Okay, cool. So there's the second derivative. Now, couple things to do here. Desmos really nice, but there's like really no way. Like if that was like not a nice number, there really isn't an easy way to figure this out. This is why the graphing calculator on TI is actually a little bit better. So I'm going to pull this up and kind of show you guys some tricks that you can do here. All right, let me pause the video until it pops up. Okay, so we got our graph here. We can go ahead, click graph, and it looks the same on Desmos. Now, what the Texas Instrument calculator can do is graph the first and second derivative. Now, to graph the first derivative here, we can press math here, and we can go down to choice 8, the end derive. And if you remember, we can do dx, and then to cheat here, instead of typing in this equation over again, if we press vars, go to y vars and press function y1, it takes the equation that's in y1 and just replaces it there as a variable and make x equal x. And so if we graph here, this red line is the first derivative. So you can see the graph is going up and it's keep going up, and then switching right here at 0, it goes to going down, and it's all negative. So the graph goes up and then it switches to going down. Now, where we can go through and check this out, we can actually graph the second derivative. And to do that, we're just going to go to this third line here, and we're going to press math again and go end derive. And what we're going to do, there we go, kind of froze a little bit. We're going to press x here, ddx, and now what we're going to do is to take vars and go to y vars function, and we're going to pick y2. So what this will do is take the derivative of the y2 equation, which is the derivative of the y1 equation. So it's the derivative of the derivative. Now, the calculator doesn't work as nicely as like doing the formulas here, but we can actually go through and we can check this out and click graph. And you can see it crosses here, kind of barely, but you can see it crosses here at -1 and it crosses here at +1. So that's where it equals 0. The other thing that I like to do in this is, sometimes these graphs get a little confusing. So I can turn off this graph. I can turn it off by highlighting the equal sign and pressing enter. You can still see the original graph pop up, or the graph you want. So it doesn't delete the equation. It just turns the graph off. Now, what I like to do is, like, we got that pretty scary looking derivative. What we can do here is, if I type it in, and I believe it was like, let's see, it was a 36x squared, x squared. Oh, really messing up now. Let me just clear this out. Let's try this again. 36x squared minus 36, and then divided by x squared plus 3 cubed. Okay, so that's what we had as the equation. What I'm going to do is I'm going to graph this as well as with the derivative of the derivative. And if they line up perfectly, that means we did the second derivative correctly. And you can see it lined it up perfectly with that. It's overlaying. So we know we did the second derivative correctly. So another way we kind of double check those crazy answers. Okay, so let's look at your homework tonight here. Your homework is to do worksheet A. And most of it, you guys are going to determine open intervals. So just like we did with these problems here. So you're going to take the second derivative and you're going to figure out where the second derivative equals 0. You're going to determine whether it's concave up or concave down. Now feel free to use a graphing calculator to kind of help you out, especially like with some of these trig functions here. You might want to go through and just use that. But yeah. Now some of these graphs here, I will give you just like a hint. If you had like a graph of a parabola, like just a parabola looking shape, if you took the second derivative of that, you probably won't get an answer where it equals 0, because the parabola is always concave up. So you might just get some of those answers that the second derivative is always positive or it's always negative, which can happen. Okay, if you guys have any questions, just ask. If not, I will see you guys for the next part where we talk about points of inflection. Have a good one.